Well, welcome everyone. My name is Meredith Elbaum. I'm the Executive Director at Built Environment Plus. Built Environment Plus is the formerly known as the U.S. Green Building Council of Massachusetts. Why the plus? Because we are also the local collaborative for the International Living Future Institute, as well as having partnerships with WELL. We work often with Hank and others at the Passive House Institute, and it's all about partnerships. And so today's event is a partnership uh, is a partnership between a few organizations. We welcome Natural Systems Utilities as our sponsor for today's event. And we're here to talk about deep dive into in design towards net zero water and the water energy nexus. At first, when Bruce brought this up as water energy nexus, I'm like, what are you talking about? I'm like, oh yeah, the overlap between water and energy. So important, and it's something that it's a huge opportunity, and I'm hoping that we come out of this and learn more about what that is. So this is the third, session of our triad on water. We started off at the R.W. Kern Center, learning about this concept of zero water. Then we went into the city and we learned about how to recycle water and how to reuse and how you would reuse water in the city. We had our tour guides were actually drank the water at the end. Apparently, that's drinkable, which is cool. Hey, Diane, can you send a link to Jim Newman for the event for today? He seems to have forgotten his invite, and I can't send him a link right now.
Absolutely.
Thank you. Anyways, so I wanted to tell you a couple things before we go on here. Hold on, just give me 1 second. Okay. This is going to be what we're doing for today. We're going to have an introduction to the water energy nexus. We're going to have a tour of a thermal energy recovery system and the thermal energy recovery system performance data. We're going to look at evaporative cooling towers. You can see this. Eventually, we're going to end up on the tour of a green roof, and then we're going to have a panel discussions with questions and answers. A couple housekeeping things to go on to. One is we pride ourselves on Built Environment Plus being a community, and so we encourage everyone to leave your cameras on if you can. It's really nice for the speakers to be able to see people going, oh yeah, I hear what you're saying, or if they're like you don't know what they're saying, like really looking confused. If not, that's understandable, but it's nice to see friends and get to meet new people. We will be going in and out of breakout sessions. There's a breakout session that's going to happen right after this, and so be prepared to turn your camera on for that and your mic ons for that right after I end talking. We also like to keep the chat up, so to use the chat in here. Dan said I'm a hero for learning about Zoom tricks. And I think you go online and look at YouTube is how I learned my Zoom tricks. Anyways, so keep the chat up. If you like, and I encourage everyone to ask questions in the chat, to talk to each other in the chat. It's a really great resource to enhance the opportunity. Although I know that some of you find the chat distracting, and if that's the case for you, then turn it off and just leave it closed. If you need any help while you're here, our friend Ethan is running the show behind the scenes, so look him up in the direct chat and direct message him, and he can help you out. If you have any questions, contact us after. We've got Diane Tufts and Jim Newman here who run our Living Future Collaborative of New England. If you're interested in getting more involved with them, send them, there goes Jim, send them a direct chat and you can help. Bruce is an active member in that group and set up this event for today as part of our Living Future Collaborative. And with that, I think I've said everything that I need to say so far. We're going to dive right into a breakout room, and we have a question for you that I am right here. We're going to break out into small rooms. I'm going to say that you can see you can see the poll results. We've got a lot of people focused on sustainability here, and then a nice mix between planning, architecture, engineering, construction, operations, and others. One last thing I want to say now that we have some more people on here too is Ethan keeps dropping into the chat our attendance form. It's not only an attendance form because we know who's here, it's really to get your AIA and CEU credits, and we have AIA, GBCI, and you can self-report for LFA credits. The attendance form also we send to the International Living Future Institute, so they know who's coming to our events that are associated with their work. So with that, breakout session number 1, we're gonna go into some small groups. This is just gonna be 5 minutes, 3 people, and talk about what inspired you to come here. And I will say that the person who has the most pets over the course of their lifetimes is the person who's going to talk first, and then they'll just pass the baton to the next person. Ready, set, go. So I hope that was fun. I know I got to meet some new people, some right around the corner and some not so close. So here we go. We're gonna, next up, going back 1 slide, 2 slides, we've got a full panel today. Experts we've got Sheng Chu from Natural Systems Utilities, who's gonna tell us about the systems that they have. Mike Redfern from Homemeyer Consulting Services, along with Zach Gallagher, who's going to be helping us with our tour of the building. And then Bruce Douglas from Natural System Utilities also, and myself are going to be your MCs and facilitators for today. Again, I encourage you, I'm looking to see how many people are here right now, 31 participants. Again, suggesting that you keep cameras on if you can, use the chat if you can, and also fill out the continuing education credits. So I am going to pass it on, and here we go. Oops, there you go.
All right, well, great. Thank you, Meredith, and thanks to everyone for coming. It's really exciting to be here. So first of all, just for those, either those who are here to get their lead professional credits, this is some of the context that you put in, but those involved in projects, you know, the LEED is a way to recognize sustainability in green building. It's very commonly used in many cities. It's the baseline of building code and compliance. And so there's 2 areas for this discussion today: water efficiency with on-site water reuse and appropriate use of that on-site water and documentation of it. We can meet all of the water efficiency credits. And then with energy and atmosphere, you know, meeting the prerequisites are met, that what we're really looking at is optimizing energy performance. And if anyone else has any other ideas or any other experience of how to capture thermal energy recovery under the energy and atmosphere section of LEED certification, feel free to write that into the chat. But at a minimum, this is what you can strive towards. So first, I'll start with the introduction to the Water Energy Nexus, which is a really big thing. and this is it's 10 years old, this document, so don't try to read the numbers, but I'll kind of describe this. This is a Sankey chart by the Department of Energy looking at the concept of this water and energy nexus. Where are our water and energy coming from? What are they being used for? And how are they being used in what sectors? And where do they go at the end? So basically from left to right, and energy is in the upper left-hand corner in the green shades, water in the lower left-hand corner in the blue shades. And with the Sankey diagram, the thickness of the bar is the proportion of that amount of that energy that's flowing, whether it be or water. And so the units, for example, are in quadrillion BTUs per year or quads, or billions of gallons per day of water. So huge amounts of water in this country. What I want to focus on, though, is the residential and commercial urban buildings, and we'll be touring a residential high-rise shortly. And where do their water and energy primarily come from? That for the aspects of we'll be talking about. So we're really trying to narrow this down to give you an example of the water energy nexus. So in energy, in all the hexagon shapes are energy related elements, and then the ovals are water related elements. So there's natural gas and electricity generation on the upper left, and flow into residential, water, and commercial, and then going to the upper right, you see that energy is used for either energy services or dissipated energy. So what's really striking here is the upper right-hand side, that gray bar at the end of the flow chart, is dissipated energy is more than the energy services that are provided. So basically, it's roughly 60-40, say 60-37 actually, it looks like. So basically, more energy is lost than is used, which is, I think, very significant. And looking at water, taking the fresh surface water in the lower left, kind of running that through a public water supply where potable water is provided to cities, through the residential commercial sector. Then we have, it's typically treated and then discharged to the surface. So it's the majority of the country, it's a linear diagram in both water and energy. And how can we rethink this and increase efficiency? We can fade all the details in the background. I kept the circles and hexagons here, but if you look, we can recycle the water and energy at a building or district scale to get the most efficiency. If you have this the long diagram kind of is good. This shows that you have a significant pathway and to wait till you get to the end to recycle your water and send it all the way back upstream is inefficient. Similarly with energy, if you can do it tight, close to where you're using it, you can really maximize efficiency, and that's what we will be talking about today: on-site water use and energy recovery at a building, and this could be replicated at a district scale, multiple buildings in a city. So this is not a one-off thing. It's a concept that's people have been working on of how to utilize water, reclaim water in a building scale, and also collect energy. So this is a 2019 cover page of an EPA report that was done, a life cycle assessment and cost of looking at distributed non-potable water reuse. And what I really like is the diagram on the right. Again, way too much information, the print's too small and fuzzy, but there's two green boxes in there. The upper green box in the middle is saying, you displace potable water treatment and delivery by reusing water for laundry, toilet flushing, and irrigation. That's very relevant to what we're talking about today. And then the green box in the lower right-hand corner, right there you go, is displace natural gas for water heating. So basically, and follow that arrow up to the building water heater, and then off to the left, follow that arrow, right there is a heat pump. So basically, in this schematic diagram, they're taking heat off of the water before they treat it with a membrane bioreactor, and then it goes into the reuse system. So it's a little different than what we'll be talking about. We'll be taking it from after the heat pump. If you look in the upper right-hand corner, there's a place below that. There's a recycled water pumping and storage circle right there, to the left of the pump. And so that's what we're going to be capturing from. So there's many ways to address this issue. What we like is the clean, clear nature of the reclaimed water. It's really efficient way to gather the energy, to recover the thermal energy, and you don't have to deal with the biological growth and organic material clogging your and masking your heat exchangers. So quick, this slide we used in the last webinar in the series, and those are available to go back and look at. Number 2 goes into much more detail just on the on-site water treatment and reuse aspect of it. But we've added, to put the context, added down below here is the yellow block and the tank to the lower right is that we're exchanging thermal energy from the treated, the reuse water storage reservoir. We have to have a big reservoir in the building to address the diurnal fluctuations in water demand. So make sure you have enough water ready when people wake up and get ready, to go to work, to walk into their closet or their bedroom, as they do nowadays. But also when they get home, when they're preparing meals and all that, and in the evening. So there's peaks and valleys in residential settings as well as in commercial settings. That the reservoir is there. Why not extract the energy? That water's been through the building, and it's been heated. And let's go to the next slide, please. There's a lot of energy just goes into treating water, and so there's a significant demand on the energy system for wastewater treatment. And again, if we can find a ways to mitigate that, to offset it, it would be very helpful. Next slide, please. And this is a quick diagram showing an opportunity that we have, and the heating of water is a very significant means of energy consumption in a building. And in this case, it's showing an example 40,000 kilowatt hours per million gallons. So, and an architect friend of mine who may be in the room here says it's a very difficult issue to deal with trying to get a green building, sustainability, and net zero energy. How to deal with that water heating load? It is definitely a challenge, and so this is one way. Let's look at the lost heat. Can we recapture the lost heat that's available in the thermal energy that is in the water that normally would go down the drain? Can we capture it before it goes down the drain? So looking at, again, a lot of numbers, but there's a lot of sensible heat energy in wastewater. Here about 40,000 kilowatt hours per million gallons, as we saw, it goes into it on the last slide. There's also, you may have heard of the organic matter energy or chemical energy in wastewater, and that's if you can extract if you digest the concentrated solids of the wastewater and get through anaerobic digestion and get that energy to make methane and burn it around a generator. It's much smaller fraction of the energy in that water is organic. So you have to have a large treatment system that's gathering a lot of organic matter to make that cost effective. At the building or district scale, what really makes sense is capturing that sensible heat, which is about 10 times the energy that's currently used for treating the water. Go ahead. So basically, treatment in a building, it's roughly, by our experience, about 5% of the building demand, or about 350 kilowatt hours per day in the high rise, the Solaire building that we'll be talking about shortly. And just a quick about the Solaire. The Solaire was a LEED certified gold building originally when it was built in the early 2000s, and then it became a platinum building under the LEED EV assessment later in its life. So it's a great building, and they celebrate their water and energy savings. And it's part of the basically the marquee of the building as you walk up to it. But we're covering. So I'm sorry. Same slide, please. I digressed. So what we're looking at is how can we extract the sensible heat to preheat the domestic water, and we do it after the treatment system. So this reuse tank in the middle of this, the water is typically 75 to 85 degrees Fahrenheit because it's been heated up to the dishwasher, the washing machine, the showers, the sinks, the laundry. Water is heated in the building, for many of those purposes, and to capture that from clear, clean water is very, very efficient, and we can providing cooler water, so the cooling tower makes that more efficient, and as also we can reduce carbon emissions by offsetting what typically is natural gas that's used to heat the hot water. We can preheat the hot water and use less natural gas, and we can completely offset the energy required to reclaim the water. And that's what's huge, is that that electric energy for treatment can be offset. So quick, just to give you a context, Sean will be walking you through this equipment on the right, the energy recovery unit in more detail. But just before we go out to the field with Bob and Sean, is in the lower left is a reuse water tank, and that water is then flows through heat exchangers, both with the city water and with water that's circulating in a gas absorption heat pump. And that water then it flows to the water from the hydronic fluid from the gas absorption heat pumps. That's just hydronic fluid in the heat pump. That circulates another heat exchanger that goes to preheats the water for the existing water heater system. So the reuse water does not contact the hot water at all. It's a separate process. But just and Sean will come back to this diagram, and what I'll do is one more slide. Thank you. And so this summarizes the big picture, that what we're doing with on-site water reuse for non-potable demand is we can reduce the potable water demand and the water heating demand, also providing water quality improvement. There's a significant benefit of sending less water out into the sewer system and less organics into the sewer system by reducing that discharge. But again, as I mentioned, we're offsetting the reuse energy demand, and we can reduce the overall operational carbon emissions by utilizing electricity, not using as much natural gas for heating water.
Great. Thanks, Bruce. Ethan's gonna pop up a poll question for you guys to answer now. Which types of water heating systems are you most experienced in? We've got solar water heat pumps, electric hot water tanks, electric on demand, and on. So I've got, let's see what's happening in terms of experience. So far, we've got electric hot water tanks, natural gas hot water tanks. Those are neck and neck. Let's see which one's going to win. They're going up one by one. 15 to 15.
The results. Can
They're not up yet.
Okay, sorry.
And you've got a question. Are you reducing the organic load to existing sewer system, or just concentrating it in the waste sludge leaving system? Why don't you answer that in the chat so that we can jump on over to the poll, over to the tour. So why don't we take the poll down? Share results. So there you go. You see the results. Natural gas hot water tanks, number one. Hopefully we'll see over time as you the electric hot water tanks coming up, and heat pumps. I've got to tell you, I've got a heat pump water heater in my own house, and we're very happy with it. Okie doke, moving on to our tour. We're going to go on a tour of in-building thermal energy recovery systems. Oops. Are you ready for this, or we're going to the tour right now, Bruce?
Yeah, I think we're starting tour.
Okay, there you go. Do you need these slides up now, or we're highlighting Bob?
Yeah, you can go to the previous one. The tour of the, yeah, here we go. Oh.
Yeah, so Meredith, we're gonna highlight Bob first, and then Chung's gonna go through his.
Yeah.
Okay.
Hey Bob, if you can turn on your video.
So I'm gonna turn off I'm gonna stop sharing my presentation so that we're focused on Bob, correct?
Correct.
Yes, okay.
Yep.
There you go.
All right, I think guys, here we go.
There he is.
Look at that scary face. Hey, Bob.
Bob is our star operator in the city. Yeah. Bob, can you hear me? Can you hear me, Bob?
Bob is muted.
Oh.
Yes, I can.
Okay. All right. Cool. So first, welcome everyone. Welcome to the tour. Today, Bob and I are just going to show what we have installed at the Solaire for heat recovery system. So right now, I believe Bob is in the wastewater treatment room. So the Solaire has a 25,000 gallon per day on-site wastewater treatment. It's a membrane bioreactor based system. So basically the wastewater will be collected and treated on site, and the treated water will be sending back to the building for the toilet flush, irrigation, and the cooling tower makeup. So what you see here, Bob, if you could turn your camera to your right all the way towards to the treatment area. Just want to give a quick introduction on the process flow here. So on the right side is the treatment tanks, which include the anostic tank, aerobic tank, and the membrane tank. So the membrane tank, we have the permeate pump that pulls the clear treated water from membranes, and the treated permeate will go through the disinfection system, which consists of ozone and the UV. So now what you're seeing, this is the permeate pump. And Bob, can you go to the ozone and the UV system? Yes, so the permeate will go through the ozone and the UV system for the disinfection, and it then flows to the on-site water storage tank. And from the on-site water storage tank, we have this recirculation loop that constantly bring the treated water back to the upstream of the ozone and the UV system. So basically, if there's no permeation from the membrane tank, the treated water will be constantly recirculate within the disinfection system. Now, where we tap into the thermal energy recovery is on the discharge side of the UV system. What you can see here is a T valve here goes out to from the treated wastewater treatment room all the way to the domestic hot water room. And then the water going through the heat recovery system and sent back to here, and then combined with the UV discharge flowing into the treated water storage tank. So now you can see the process water supply, that arrow to the left means goes to the heat recovery system, and the process water return arrow to the right, that means the permeate is returning back to the storage tank. All right, that's good. I think we can move to the domestic water room. So now what you're seeing is the two on-site treated water storage tank. All right, just the next door, we have, this is the domestic water room, which they have the water pumps and the hot water heater. So what you're looking at is the heat recovery system that we installed. Basically, it has, essentially has two parts. The bottom part is a commercially available ammonia gas absorption heat pump. And on the top part will be the hydronic loops, expansion tanks, recirculation pumps, and the heat exchangers. So on your left side, all the processed water or the permeate, the treated, the reused water will come in on the left side, going through a series of heat exchanger and then return back to the treated water storage room. Yeah, thank you for getting into the back. what you can see, there are 3 heat exchangers installed on the back of the unit. The middle one is used for the first heat exchange between the domestic water and the reused water. And each stream will go further step to do a second step heat exchange with the hydronic loop provided by the heat pump. So as I just mentioned, the processed water is coming in and out from the left side of the heat recovery system. On the right side, where you have all the domestic water flow in, Bob, if you could point up, yes. So we tapped into the existing existing cold water supply to the existing water heater and send a portion of water through the heat recovery system. And the heated domestic water will be injected into the existing hot water supply system. Yeah, following the pipe, the injection pump, and the tie-in point will be the existing hot water supply system. Yep. Okay, so the next I want to show is Bob, if you could move your camera to the left a little bit. The 2 existing hot water heater is powered by the natural gas. It's the same, the ammonia gas absorption heat pump also is powered by the natural gas. So we track all the gas consumption by 3, using 3 separate natural gas meter just to track gas consumption before and after the installation of the heater recovery system. And if you turn your camera to right a little bit, you can see the 3 gas meters are installed. These are 2, one for one of the existing water heater, the other one is for the heater recovery system. And there is another gas meter installed on the other side of the water heater. So now going back to the heater recovery unit. And this is the control panel. We have the PLC-based control panel and the HMI that you can monitor all the temperature and the pressure and change the operation mode. And to integrate the system into the existing infrastructure, one aspect is the exhaust. So the exhaust of the heater recovery system, which is on the left side. Bob, if you can rotate the camera to the other side of heater recovery system, yeah. So that's the exhaust that we tie into the existing exhaust duct from the water heater. And also we did some control integration, the PLC integration with the existing wastewater treatment plant and the integration of into the BMS system into the fire alarm system. So also for the safety setup, we have, since this is an ammonia gas absorption heat pump, we have the ammonia detector, which is linked to the alarm. And also we have the natural gas detector. All right. So that's the general setup of the system here. Thank you, Bob.
Okay.
Okay. All right. Cool. So before I start presenting some of the performance result from the heater recovery system, I want to touch a little bit on other energy optimization project that we conducted at the Solaire This is for the wastewater treatment side. As Bruce, excuse me, as Bruce mentioned in the previous slides, the energy consumption for 25,000 gallon per day on-site reuse water system is about 350 kilowatts hour per day, which is about 5% of the building energy demand. And among those energy consumption, the aeration occupies about over 50% of the energy consumption. So, we're thinking about, how to reduce the energy consumption, how to optimize the energy utilization for an on-site water reuse system. The key thing is to reduce the energy consumption from the aeration. So we conducted a couple of modifications to the existing treatment process, such as separating the aeration supply to the membrane tank and the aeration tank, and also modify the operation operation mode to the existing blower. We will be able to reduce the energy cost for the on-site water reuse system. If you go to the next slide, before the process optimization, we're seeing constantly 350 kilowatt hour per day on the energy consumption. After modifying the operation of the blower, we are able to reduce the energy consumption by 18%. So now the treatment plant consume about 300 kilowatts hour per day on the energy. And the specific energy in terms of kilowatts hour per 1,000 gallon is reduced to 10, around 10. That is about 23% of energy reduction. So now going back to the thermal energy recovery, what you just saw is what's reflected on this ski diagram. So we're taking the reused water sending through multiple heat exchanger, and the heat will be extracted and passed on to the domestic hot water. So the heat transfer is achieved by 3 heat exchanger and ammonia gas absorption heat pump. So to monitoring performance, we installed a lot of sensors and meters to measure the temperature, pressure, flow rate, gas usage. Also, we have the PLC to track how long the heat recovery system will run on the daily basis. So this is the current scheme, that current operation condition we're using. Currently, we're sending about 3 to 5 GPM domestic water through the heat recovery system, and the heat up to about 100 to 110 Fahrenheit going into the hot water, existing hot water heater. And on the reuse side, we are able to extract about 10-20 Fahrenheit difference with a flow of 8 to 10 GPM. So what we've seen so far is when the heat pump is in operation, we are observing this 12% of nitrogen gas reduction just by comparing to before the operation of the heat recovery system. And over the year, we're seeing on average about 930 cubic feet natural gas reduction. And because this is a residential building and the hot water demand is not needed all the time, 24 hours, 7 days. So the heat recovery pump only runs about 50 to 60% of the time. If there is some application that requires the hot water, 24 hours, we would expect more natural gas reduction. So now we bring the whole picture together with the on-site wastewater treatment system plus the heat energy recovery unit. With a combination of the process optimization and the thermal energy recovery, we are able to achieve a net energy neutral or even net energy positive case at a high-res residential building scale applications. So now I want to talk about a little bit on the economic impact on the project that we have here. For the process optimization, we're looking at a capital cost about $10,000 to $20,000 to modify the system, including adding a additional small blower for the aeration and some control integration. And based on the energy saving, we're saving about $400 per year on the electric bill, which turns to 25 to 5 years on the ROI. So for the heat energy recovery, since this is the first of its kind, and this is demonstration plant, and it's a retrofit, and we are experiencing additional work dealing with the labor, material design, and the permitting, the overall capital cost. Okay, all right, we're back on track. So we are expecting about $190,000 for the capital cost on installing the system. But the primary goal for here is to confirm if the net energy neutrality can be achieved on the high-rise building applications, and we are approving that it can be. So if this is a new system and for the future installation, the cost will be lower to $75,000 to $100,000, and depends on what type of energy source you are using to your water heater, either natural gas or electricity. We will have the different ROI based on the type of fuel. So now Zach will talk about on the economic of the on-site water reuse.
Sure, thanks, Sean. This was presented during the last session, and we just wanted to connect the dots here. Sean gave you the ROI for the thermal energy recovery unit, but we use general rules of thumb for the overall payback and where it is cost effective to look at these systems. So on the top chart here, you can see that red line is showing you where certain cities are at or above a typical $12 per 1,000 gallons for the cost of water and sewer. So another way to say this is if in your local area, your cost to receive your water from that centralized provider or that utility that's providing your water, and the cost to treat your sewer is at or above $12 per 1,000 gallons, it's generally cost effective to start taking a look at on-site or decentralized water reuse from a straight economics perspective. And so you can see those cities where that is above, and this chart is a little bit dated, and these water prices are changing pretty rapidly. So that bottom graph is showing you that in many coastal urban city centers, the cost for water and sewer has more than doubled over the past 10 years. So you can see the percentages annually, but if you go back over the past 10, 15 years, this is showing a larger track than that. You can see that the cost for water and sewer is far outpacing inflation as we have our source constraints or centralized sewer constraints, and we need to repair our infrastructure, if you will. So we need to start to work together to find that resiliency, find that right balance, and these rules of thumbs can kind of help you target where you should start looking at on-site water reuse systems in general, and then where you should start adding thermal energy recovery. Go ahead.
Okay, we are going to dive into our breakout session number 2. It's an opportunity for you all to discuss some of your challenges that you're seeing in incorporating water reuse with your thermal energy recovery for your projects. So these are going to be a little bit bigger groups. We're going to have 6 people in the groups. Again, we want to talk about what are the challenges, like why wouldn't you do this in the next project that you're working on. And so these are going to be a slightly longer discussion at 10 minutes, and then we're going to come back for another tour.
Okay, so well, that's an attractive site, and to some people that's considered gold. All that extra water. someday that water is going to be extremely expensive, and I think Natural Systems has a real good gig going on with taking water sources, reclaiming it, processing it, and using it again. So one of the big questions is, where do you get rid of all this water? And a few of the comments were, flushing toilets and irrigation. But one of the biggest consumers in cooling tower, well, I just gave it up, the cooling towers in buildings and process are cooling towers. They consume a ton of water. Cooling towers, as you know, they extract heat from process or from HVAC systems, and they evaporate the heat through these devices. And by doing that, they lose a lot of water through evaporation. They also blow down water to control the amount of solids in the system and minimize scaling and corrosion. So if we're looking at one of our clients is One World Trade Center in New York City, they use about 17 million gallons a year in their cooling tower system. It's a considerable amount of water. They also have a reclaim system, which we'll talk about in a second. But this is one place. The problem is that cooling tower systems are generally designed and treatment-wise with a consistent makeup. And sometimes when you're using reclaimed water, you get a lot of variabilities. You don't know what consistency the water is going to be today as it is going to be in another season. And you set up your programs designed around a specific makeup quality. Next slide. So we talk about treatment goals of a cooling tower system. You're looking at different water qualities, and water being the universal solvent, meaning that the water doesn't have minerals it wants to make up. And it could be piping, it could be calcium, magnesium, that it's trying to make up for what it doesn't have. That's a corrosive water. Pure water is considered corrosive. It wants to dissolve things. Hard water, on the other hand, can be scaling. And you oversaturate that water, you can precipitate out hardness and impede heat transfer on heat exchangers by scaling them up. And just go back 1 second. So the goals of treating a cooling tower system obviously is to minimize scale, corrosion, biological fouling. Bacteria is a leading cause of premature failure in systems. Bacteria can actually cause corrosion. And then you have the human health factor, like Legionnaire's disease and Legionella. So those are some of the things that are goals that you're trying to accomplish when you're treating a cooling tower system. Okay, next one. So AWS stands for Alternative Water Source. That's what New York City terms a water source, a makeup source of the cooling towers. That's anything but municipal city water. And alternative water source could be a combination of things. It could be black water, it could be storm water, it could be steam condensate. And like I said, treatment systems for cooling towers are designed around a consistent makeup. When a water treatment company puts in their chemical program, it's designed around the quality of makeup that's going to that cooling tower. Reclaimed water can vary depending on season, depending on demand, or what sources they're pulling from. And then how many sources contribute to the makeup. The more sources, the more complex that water is at protecting. And we just talked about all the savings that you can achieve through reclaimed water in the process of, processing black water and all the energy savings. We certainly don't want to pass that on to a cooling tower system through failures and having to replace things just because we want to use this makeup water. It can be used, but there are some challenges. For example, the black water has a considerable amount of phosphate in it. Humans generate in waste a considerable amount of phosphate, or irrigation, stormwater that's possibly washing off surfaces that have been cleaned with detergents. All that phosphate gets into the reclaim tanks, and phosphate is actually a good corrosion inhibitor when it's fed at small doses. At a large quantity, it likes to bind to other elements like calcium and iron and form deposits. And that can form deposits on heat exchangers and again, eventually impede heat transfer. pH is always a challenge at times. If you're using steam condensate, it's pure water, and you steam condensate from makeup to the cooling tower, that condensate is going to be very aggressive and the pH is going to be low. So we got to do something to that. Hardness, again, we talk about keep saying irrigation, but stormwater or rainwater that's washing off plaza level, that's concrete, and it's bringing that hardness, the calcium and magnesium from concrete into the reclaim tanks. And hardness, again, can be a form of scale in the system. Biological nutrients, you know, if you have any type of fertilization going on near lawns and vegetation, you know, you get some of that storm water and you're dragging that into the reclaim. Those nutrients can act as a catalyst for bacterial growth. So, and then more suspended solids. Suspended solids will accumulate in cooling towers as you evaporate, and eventually, if it's not controlled, you can also have problems that way as well. Chloride salts are also very corrosive. So there's a lot of different challenges depending on what makeup source you need to take these challenges and determine what's the best treatment approach. And some of the solutions that we've used for the Solaire years ago, we determined that there was a considerable amount of phosphate that was depositing on absorption chiller, condenser tubes, and absorber tube. And we came up with a plan with Natural Systems to feed aluminum chlorohydrate to help precipitate that in the process, in the waste treatment process, and eliminate the phosphate from becoming a problem in the system. pH adjustment was used sodium hydroxide in systems that are using a considerable amount of steam condensate for the makeup to try and raise that pH and make it less corrosive. Filtration for suspended solids is always a good tool, and that's sometimes used in a system that's not black water reclaim, but more of using stormwater and condensate. UV light, ozone, and chlorine dioxide have all been used in the waste treatment process as well, or the reclaim process, to minimize bacterial growth. Next slide. So here's a line drawing of the One World Trade Center reclaim system. And it starts down at the C2 level. This is a 103-story building. The C2 level has 3 100,000 gallon reclaim tanks. And what they collect is stormwater, rainwater from the roof drains. They have rainwater collection from the plaza around the building. They have steam condensate that they collect, and also coil condensation. And their cooling tower system is fairly large. It's it'll use about 17 million gallons a year of makeup. Of that, there's probably about 4 million gallons that comes from the condensate and the reclaimed water sources. So from the C2 level, that gets pumped, and I'll talk about where that water goes first. That gets pumped to intermediate tanks on the 57th floor, these two 50,000 gallon storage tanks. And from there, it gets pumped up to the 93rd floor storage tanks, where it goes through a secondary treatment before it finally is made up to the cooling tower. So down on C2, what we had to do is they have a recirc loop taking from the 300,000 gallon tanks. It goes through filtration, UV system, and then back to the tanks. It also has a smart controller that's tied to this loop that measures ORP, conductivity, pH, and turbidity. And it has, programmed into the conductivity controller, where we'll control the conductivity. If it ever gets above 400 micromoles, it'll blow down just because of, just controlling the chemistry in the cooling tower and what we're going to achieve for a reclaimed system going up there. We had to have some type of consistency with this makeup source, but also the ORP controls chlorine dioxide unit, a one precursor chlorine dioxide system that helps for a secondary disinfection on these tanks. And all this water that goes through this pipe all the way up to the 57th floor, you've got to be concerned about regrowth. So there's always a residual chlorine dioxide in this water. And then as it gets pumped to the 93rd floor, there's another secondary or tertiary treatment system that also has a smart controller and monitors ORP, connectivity, pH, and turbidity. And it also controls a chlorine generator using the salt chlorine generator unit, and tries to maintain about 0.5 ppm of free chlorine, again, to minimize secondary growth in these tanks and all the way up to the cooling tower. So if you're not aware of it, New York City does have a Legionella law, and they required a water safety plan, not only on the cooling tower, but also on this reclaim system.
That's great, Mike. Thank you. And Ethan, if you could spotlight Bob again, we're going to go up to the towers and show everybody the towers. And Mike covered a lot of what I had to say, so we'll probably make up some time here, and I'll just show you the instruments. Hey, Bob is back. All right, Bob, if you could turn your camera the other way around, great. All right, so Bob is now up at the cooling tower. Bob, if you actually can just do a slow circle around, show them the entire room. Nope, go horizontally up and show them the entire room. So he's up in the cooling tower, and if you haven't seen a cooling tower area before, so keep going, just circle around. Yep. All right, so when Mike viewed his overall diagram of the cooling tower, we'll go outside and see the cooling tower. Just turn to your right, Bob. Yep. Okay. So what you're seeing here is the system that was on the right side of Mike's diagram, right? And so it's a combination of chillers, heat exchangers that are part of the overall cooling tower system. And so we are feeding reclaimed water up to the cooling tower in this cooling tower system. The tower is outside. You'll see that in a second, but these are the combination of chillers and heat exchangers. And so it's really important to talk early with your cooling tower consultant, because there's various forms of cooling towers that can be used. At the Solaire here, we have a shell and tube heat exchanger. Other buildings, we have, flat plate heat exchangers, and some of them are more resilient to different types of water quality. So as we're talking about this water energy nexus, and as you've heard from Mike, these connections go far beyond thermal energy recovery. We also are looking at feeding reclaimed water up into the cooling tower, and we can do that more water efficient. We can do that more energy efficient, and it's how we actually integrate these technologies together. All right, so the evaporative cooling towers use a lot of water. All right, they if you saw in the last presentation, we use just as much water to heat and cool the Solaire building as everything else in the building combined. We could be using 30,000 gallons a day in the cooling tower for makeup water, when the entire rest of the building is using 20 or 25,000 gallons a day, especially during the peak summertime months. So this is a real good opportunity to reduce your water footprint. But as Mike said, you have to do it properly. All right. So Bob, if you turn back to the blending valve. So Mike spoke about phosphates and controlling phosphates. So very early on, when we started the Solaire, we were getting orthophosphate deposition on the heat exchangers. And so what we did was we incorporated a blending valve initially, and we have a potable water source coming from New York City, and we have our reclaimed water source coming up into the tower to feed its makeup water. All right, and so that orange valve that you see there is a blending valve that we can decide we want 30% reuse, we want 70% potable, or vice versa. And we went through a 2-year study with NYSERDA, New York State Energy Research Development Authority, to figure out exactly what the cooling towers needed and how we could control that within the rotor reuse system, so that we could use as much water as possible within the cooling towers. And so we started, as Mike said, adding aluminum chlorohydrate down in the water reuse treatment system, getting our phosphorus levels to 1 to 2 milligrams per liter, sometimes less than 1, controlling that orthophosphate, and looking at all the other parameters and getting 100% reclaimed water into the towers without concerns of long-term degradation on these heat exchangers. So again, we have the ability to blend that, but the goal was to get to 100% reclaimed water. We did achieve that, and it really depends on how your cooling tower is set up and how your program with your cooling tower consultant is coordinated. All right, so with that, Bob, why don't you go ahead and head out to the green roof and the cooling tower area. And Ethan, do you want to show your poll question as Bob's walking out? There you go. All right, so as Bob's walking out, why don't you guys go ahead and read that poll question and answer that, and then we'll keep the tour going. Bob, why don't you walk around the building the other way? Yep, there you go. And then just turn around that corner and look through the screen, and you'll see the cooling tower, very similar to the diagram that Mike just showed. And just look up from there. Okay, so I know it's hard to see. You can kind of see the screen. You can see where the air goes into the sides of the cooling tower. Okay, there's a fan on top that's drawing that air through. As the air is drawn through the cooling tower, you are dropping your water droplets down and exchanging the heat from the building and evaporating out to the atmosphere. Okay, and what that does is it cools the water coming down, and then you're recirculating that water back into the system that you just saw. And so not only does the thermal energy recovery system extract the energy to make this water reuse system net energy neutral, it also provides a lower temperature water going up to the cooling tower, which increases the efficiency of the cooling tower. Obviously, if you have cooler water, you're going to get better heat transfer, better efficiency of the tower itself. So that's how all this is connected in terms of the water energy nexus and making these things as efficient as possible, both on the water side and on the energy side. All right, Bob, so why don't you keep walking around? We're going to show the results from the poll. And let's go over to look at the 13th floor green roof. So just go to the other corner of the building there. And let's look at the green roof and Teardrop Park. Evaporative cooling is the highest here. That's great. We also saw electric versus gas on the previous poll. So good mix here. Okay. All right, so now you're seeing, well, first off, that's the Hudson River. All right, so you're seeing at the top of Bob's camera, Hudson River, that is New Jersey. Okay, and if you, we'll turn the corner, you guys can see the Statue of Liberty and Ellis Island and all that good stuff as well. But Bob, if you look down at the green roof for a second. Okay, so as Mike was talking, really depends on your source of water and what's in that source of water and how you treat that, how you can optimize its use in the cooling tower. At the Solaire and all of the other Battery Park City buildings, we have both stormwater reuse in addition to black water reuse. Some of these reuse systems are integrated, where we can take that stormwater and send it into the black water treatment room to get as much source water as possible during certain times of the year. And then this treated water is used to irrigate the green roof here on the 13th floor. In addition to Teardrop Park, Bob, Ethan, is Bob's camera frozen?
Yeah, it looks that way to me.
Yeah, I don't think Bob can hold it that steady. But that's okay. If we get Bob's camera back, that's okay. Otherwise, this was the end of, oh, there we go. Good. So Bob's camera is now moving. So Bob, if you could show Teardrop Park as well, just kind of circle over. Yeah, maybe the reception in that area is not great. So not only does this reuse system provide reclaimed water for irrigation of the rooftop garden, it also provides reclaimed water for the entire Teardrop Park between this block of 4 buildings within Battery Park City. We also send water over to the Verdesian, which Bob is looking at right now. So we collect all of the wastewater from the Solaire, we treat it, we send it out for irrigation water to Teardrop Park, in addition to the green roof on the 13th floor, and also over to the Verdesian for flush water as well. So it really is a two kind of building system, and it's used for multiple purposes. And we collect the stormwater, rainwater as well, and we treat and reuse that. We have a separate treatment system for the stormwater. It is a separated where it's just filtration and disinfection, and then used back for irrigation. Or we can send that source reclaimed water of stormwater into the main treatment room as well, and use it for cooling tower and flush water reuse as well. All right, Bob, thank you very much. I think from there, Ethan, we can get on with the rest of the agenda.
And next up is our panel discussion. Bruce, I think, is going to kick it off with some questions.
There we go. Yeah, I guess a couple of questions that have come up, and the one just came up was the from Bradley, and either Jack or Mike, the cost of the alum chlorohydrate and what do we do with the precipitate? Aluminum chlorohydrate.
Sure. So I'll start with there. The aluminum chlorohydrate feed goes directly into the membrane bioreactor itself. The cost that we are currently getting for the alum, I'm not sure. Mike may be able to reference that directly on the cost for the alum. But what we're doing is we're adding an alum feed where we control the amount of orthophosphate that we're getting through the system that does precipitate basically into the sludge. And that sludge is managed with our mixed liquor suspended solid. So as the membrane bioreactor will get to 12,000, 13,000 milligrams per liter, we will waste that sludge. That was part of the organic kind of question early on in this session. That goes out to the city, and it is discharged about once every couple of weeks, because we're able to maintain this membrane bioreactor from 7,000 milligrams per liter to 13,000 milligrams per liter. So we do it manually as we waste. It is only done when it is not raining, so we don't attribute any organic loading into the sewer during any potential combined sewer overflow events. And that mixed liquor suspended solids is roughly about 1 to 2% solids. It flows by gravity. So the municipality, the city, really saw it as a very symbiotic relationship where we didn't need sludge holding tanks, but at the same time, they got some of that organic loading because, as one of the comments said, they do have a very dilute influent with a lot of infiltration and inflow. So that's how it's managed. Mike, do you know the cost that we're currently getting at Solaire for the alum?
I don't. It's cheap. The stuff is cheap, and you don't use that much. I can get a cost for you.
Great.
So I've got a question for you guys.
Yeah, go ahead, Meredith. Yep.
It is following up on Nicole's question, right? As we are looking at net zero, and there's debate around the net zero stretch code potentially in Massachusetts right now, and thinking about the future and thinking about a push for electrification. We know that the systems that we looked at were gas fired, and I guess my question is what's the future? What does the future look like in terms of electrification of these systems? Is the technology coming? How far out do we think it is? Is it feasible?
Sean, why don't you go?
Yeah, sure. I think electricity powered heat pump is out there. So actually, when we first started, we look at a couple options there. Like I said, in the chat is, the reason why we stay away from electrified heat pump is first, it's cost more on the energy consumption, and it's cost more on the capital investment. And well, it's doable, but I would think you need to do analysis on the energy balance. Say using the electric pump, how much you can extract from the heat and how much you can offset by those amount of extracted heat. So I would say it's doable, but analysis to the system need to be conducted.
Yeah, and I would only add to that, Meredith, from a overall triple bottom line standpoint, typically you see lower costs for natural gas than you do for electricity as you're balancing it with the efficiencies. So in terms of what we needed here, it would have decreased the ROI going that way. So again, it's all about balancing what you're getting from an energy water efficiency standpoint, but also looking at the ROI and the cost effectiveness of these elements as well.
And I'll add to that. I spent a good part of last week at a campus district energy conference, and a lot of college campuses are going, with a decarbonization strategy. Some from 2030, some as far out as 2050. But in doing so, they're also seeing transitions. Is what can they do to transition to recognizing they can't necessarily do it tomorrow. And a lot of it is putting in geothermal, geo-exchange wells and whatnot on campus. And this is a way to provide another source of energy that could be compatible or offset the use of the requirement of as many other sources of heat exchange or heat pumps. I think, and as cities are now starting to mandate and require, electrical systems rather than combustion systems in buildings, that we need to make the transition, and it's really project specific, of whether the project transition is now or is this a way we can decrease the carbon footprint over time while the technology improves, and that's a very valid discussion.
Yeah.
Hi, can you hear me?
Yep, go ahead.
Hi, this is Sissy Ma from EPA. I'm actually the PI for that EPA report you're referring earlier, and I just want to mention that we just released a tool, the non-potable on-site non-potable water use tool yesterday. So the question about the electricity use, the electrify the system, it really depends on the regional e-grid, the electricity grid, the mix. So if you're in a high carbon grid, you're using electricity it's probably not good. But in the region of New York, you pretty much have a clean grid. So using electricity for the heat pump might be beneficial. So you actually have to take into account everything and analyze. I was wondering, you guys did a wonderful job. I was wondering about, have you analyzed like the global warming potential type of environmental benefits on top of the cost?
We did, and Shung can get into more details here. So as we were designing the thermal energy recovery unit, there's obviously multiple transfer fluids that you could have used. We decided to go with an ammonia-based heat pump because of the greenhouse gas benefits of it. And so when we looked at the overall greenhouse gas and carbon benefit, this was the most efficient system that we could design from a greenhouse gas standpoint. Not that the approvals for another type of system would have been a lot easier. We had some challenges going through the fire department on the ammonia-based heat pump, but it was the most environmentally responsible, I should say, way to do this. And so we're balancing that as we go into other cities and what transfer fluids are being used or direct heat exchange. So there's variations of the ways that you could do this, but that's the way it was done in New York City for this one because of the greenhouse gas benefits. Shung, you want to add anything to that?
I just want to add.
Yeah, go ahead.
I want to add your comments here. It's wonderful that you consider the heat pump here. When we did analysis on different kind of membrane MBRs, aerobic MBRs, spodulate or continuous running, and with for example, constructed wetlands. So it actually turns out the thermal recovery does make a big difference. but I think that's a direct benefit. The another one that didn't capture, or maybe if you should think about for the cities, is you offset the drinking water. The delivery, the treatment of the drinking water, that benefit for the carbon offset is quite a big too. So I know the city of New York is actually trying to do something, do their analysis on this. We work with them a little bit.
100%.
So it will be,
Yeah.
it will be good to compare, say, how much energy from avoiding the drinking water versus other energy saving. For example, the thermal recovery.
Correct. We got into this a little bit in our breakout session, but that's exactly why we did this. You look back 20 years ago when we were starting to do these water reuse systems inside buildings in Battery Park City, and the skepticism about some of the on-site reuse systems were how much energy are you using to recover a gallon of water? And what is the water energy benefit and the overall carbon benefit as you look at these systems? And so because you have the source of heat and the demand for heat right at the building where that on-site water reuse system is, not only are you now getting all the benefits of the water reduction and that carbon footprint in terms of the centralized provision and extraction of that water, but now you're also getting the thermal energy recovery. And now you've made these on-site water reuse systems not only reducing your water footprint by 50, 60, 70%, now you are net energy neutral or net energy positive while having all of the environmental benefits of that integrated, decentralized, centralized infrastructure. So that was the goal, was of course, as an economy of scale to centralized systems and treating more water, you're going to have a better energy water profile. However, those centralized systems are typically all the way away from the community, and trying to bring that resource back, whether it's water or whether it's energy, back into the community has a huge carbon footprint, right? So let's integrate our centralized, decentralized infrastructure so that we can minimize that carbon footprint of the combined systems.
I'm gonna
I just
ask
also
folks. Sorry, I'll let you finish.
I just want to add.
Yeah.
I just want to add. It's not just the cost. I mean, last week the water crisis in Texas is showing, decentralized may play a role in the resiliency of the system. It's not just the cost. So a lot of the community are start thinking about that.
Yep.
Sorry, go ahead.
Yeah, I just wanted to ask people to please put their comments in the chat and questions. And if there's something that you would like to ask out loud, we will call for you to ask out loud just to manage the questions a little bit more. So I invite some more questions. While we're here, I did want to go back and ask Nicole if she wanted to pop in to a follow-up, since that was your question on the heat pumps and I asked it for you.
That was a great thorough answer to the question on the heat pumps. I do have another question. So noting that Battery Park is directly on the coast, are there any considerations or special accommodations that needed to be made for coastal resiliency at a project of this scale?
So not for the Battery Park City systems. There are Department of City Planning for other, we're doing a lot of systems now over in Queens that are also below the floodplain, and they're looking at it from that standpoint as well. There's no additional requirements. Nicole, I think to the point of your question is, where do these systems be best located in terms of the basements or up higher, above the floodplain and things of that nature. And so there's a lot of work that's been done, and we still put them down as low as possible, because from an energy efficiency standpoint, we're getting the benefit of that gravity, bringing that water to one place all the way down, getting as much water as possible, and then sending it back up without multiple feed and pumping systems if it were at a different elevation. And we're finding other ways to flood proof and make these systems more resilient, even when they're at lower elevations. So all of the Battery Park City buildings now use, I don't know if you've seen them, the balloon systems that can be put up in 15 minutes that actually raise that impermeable surface up 4, 8, 10 feet, depending on the size of that balloon. So a lot of those resiliency efforts are going into that. I will point out on the topic of resiliency, and I'll be quick here so we can get to other questions. When we had Superstorm Sandy come through, we had 100 systems that were in a direct influence of Superstorm Sandy. Not a single one of those decentralized systems went down or violated permit conditions, while centralized systems were down for weeks and months at a time. And it's because we have the local generators. We can keep the systems running. We have that local source and use for that water. And so it's another story to tell on the resiliency side. We're not having large horizontal pipes going through very low-lying conditions that where you have an isolated problem, you're now creating a regional challenge. And it's really a way for city stakeholders now to see the resiliency of this integration where you are in low-lying areas or floodplains and things of that nature.
So you're saying definitely waterproof of some level, the holding tank, but also make sure you have a generator on site so that that system can remain intact.
Correct.
And I think you said at the last presentation that the holding tank was concrete. Does the idea that the site might flood impact the buoyancy calculations?
It does not in terms of what we did for Battery Park City on the buoyancy side. When these things are going underwater, yes, you're pretty much, you can floodproof that door or that room if you were going that way to do that. But we were not needed or did not have required to calculate buoyancy with additional floodplain uses now.
Thank you so much.
Yep.
So I guess a question that came up earlier, Mike, you touched on it, the New York City Legionella requirements. I guess if Mike and Zach want to just touch on the issue of Legionella and the point of that reclaimed water in the building has been more recently disinfected than municipal water from far away.
Sure. Mike, you want to start? You want me to start?
Yeah. So if you don't know, New York City did adopt a law that you had to have a water safety plan for Legionella risk management on your cooling tower. And then they discovered that, some people have been taking and reclaiming water and using that for the cooling tower as well. So then they thought that, hey, that could pose a risk. When you follow the ASHRAE 188 framework, you have to go around and find all the potential risks or contributors to Legionnaire's disease that would be contributed to the cooling tower. And you're not taking municipal water, which is treated. Most of them still have a residual of secondary disinfection, chlorine or whatever in that water. But now reclaimed water, which they don't have control over, you had to develop what they call an alternative water source plan for the cooling tower that pertain to Legionella risk management. But as far as the black water systems go, the systems that Natural Systems puts together, you know what you're going to get. I mean, the final product is a disinfected, sterilized product or a water product. And when you're taking other sources that are not typically set up to treat, I mean, we had to come up with a plan to provide secondary disinfection for One World Trade Center because they were just taking stormwater, condensate, coil condensation. And, you think about where this water is running off of, the plaza, where people are, walking, and this bacteria that people are tracking around on the plaza, and that's water washing off into the reclaimed tanks and the storage tanks. It still has to be disinfected. So, we had to develop a plan to filter because more suspended solids were coming into the tanks. We had to develop a plan to make sure that water was not going to grow bacteria in the tanks or in the piping. So all that stuff had to be taken into consideration before using it for the cooling tower.
Yeah, Mike, I'll just add to that real quick from a New York City, focus perspective. Initially, in 2015, when the Legionella outbreaks occurred, the Department of Health made an initial opinion. Okay, let's shut down all alternative water source systems and not approve them going forward because we don't know where this is coming from. And so we acted quickly to provide data to show the Department of Health that not a single one of the Legionella outbreaks was connected to any of our reclaimed water systems, and provided data in terms of the level of treatment being provided, and that because we're doing the disinfection very close to the point of use, the risk is lower because you don't have time for that to regrow within the system. And it's really much more about how the cooling tower is being managed versus that source of water. So if you treat that source of water properly, it really does not matter what that source is, as long as you're treating it properly and sending it up and that cooling tower is being managed properly. That's really where the risk boils down to. And so we were able to provide that data, showed it to them, and now they said, great, we get it. And now just make sure that your systems are incorporated into the alternative water source plan from a cooling tower management program standpoint.
Thanks. Sissy raised a good question in the chat. Is there any issue for sewer system flows or scouring power if large amount of wastewater is diverted? I can begin. Just
go ahead, Bruce.
In the Boston area, we had a city where we basically talked to the city and they provided their sewer flow modeling resources that we could look at that and make sure that where we were looking at the potential for sewer mining, which is a large diversion, and we had to make sure we had to be collecting from a pipe and discharging to a pipe, that had the adequate capacity. And then, but I'll let Zach talk about just the building district scale that he's been working on.
Sure, and I think it's a two-part question, Sissy, if I understand you correctly. So, and it's a very regional answer. This is probably the big elephant in the room when we go across various cities. It really depends on how the centralized wastewater infrastructure has been set up and designed around. I think many of you have probably heard, you're stealing my sewer, right? And we're getting to a point where wastewater is a valuable resource now, and people are starting to understand that. And so really working with the centralized and decentralized infrastructure stakeholders together, one by one, as early as possible is critical. New York City had the foresight to see some of the challenges that we have with some of the leaking aqueducts that are coming into the city, some of the repairs of those aqueducts. We were going to need more sources during that repair. And they also understand that this is a capital offset for them. So if they can have on-site reuse systems, they have more water available for future users with less capital upgrades. And there's a long-term savings here to the city if we integrate that infrastructure properly. In other areas, they haven't gotten there yet. There is still, we have this massive wastewater treatment plants. We are under capacity. We need more revenue coming in for the centralized infrastructure, and you're stealing that source and that capacity. And so there's a lot of differences of opinion in those areas where the wastewater infrastructure may be set up that way. But what we're starting to see is that there's either local or state mandates coming down to reduce the water footprint of those communities, and that's being placed onto the utilities. And so rather than, even if you have a large wastewater treatment plant that has more capacity than it's currently receiving in terms of flows, they still have to have, for some areas, a requirement to reuse that water and reduce the overall water footprint of the communities they're serving. And so they now have to wrestle with either they're going to send a large purple pipe out to those communities and miles of additional infrastructure costs to do that, or they can partner with the decentralized infrastructure stakeholders and have localized water reuse rather than doing all of that horizontal infrastructure and sending that purple pipe out. So that's where we're starting to see some of those drivers where you may have enough wastewater capacity, but you still have to reduce your water footprint.
And on a related aspect of that, Zach, is the I&I mitigation. In Massachusetts, they have a fee that's required for large projects, great sewer projects greater than 15,000 gallons per day, have to pay into a infiltration and inflow mitigation fee, whether it goes into a fund or do a project of equivalent value for removing 4 gallons. You put 1 gallon in, you got to remove 4 gallons out of the combined sewer overflow system. It's often, separating the sewer, separating the stormwater pipes from the sewer pipes in the street. And cities throughout the country are doing that. They're doing their CSO project, combined sewer overflow projects, but this is one means of funding that. And we're seeing that some cities are recognizing this as the benefit of really thinking upstream. If communities put less in the sewer as opposed to trying to mitigate it after it gets into the sewer. So there's a potential for using on-site reuse to lower the I&I mitigation fee for a project. And I think that's a valuable recognition, and it does depend on city to city how they interpret that.
Yeah, water reuse used to only be talked about in the dry climates, right, Bruce? In the southwest and the southern states, and Florida and California were the drivers for water reuse, and yet Battery Park City was going on this whole time. And what we're really starting to understand, the community's understanding, is that this is not just a dry weather or a source constrained solution. This is also a very wet weather focused, where we have I&I challenges, we have combined sewer overflow challenges, and this is the way where we can manage that wet weather impact.
Yeah, and what Jacob said in the chat about the Boston Water and Sewer Commission welcoming reduction of sewer effluent in new buildings, they have expressed to me that's a preference for that. They're not dependent on fees from buildings that haven't been built yet, but they are concerned about taking away customers. So the sewer mining is going to be more of a challenge, for example, in Boston, but the Boston Water and Sewer doesn't see an issue with reducing the flow into the sewer as long as it's properly, compatible with the design of the sewer, which is analysis that would happen with any building and any sewer discharge.
Can I make a comment here? We were working with Lawrence, Massachusetts, so their model might be an alternative, so the cities don't have to fight if the flow is low. They actually co-digest the wastewater with other source of higher organic flows, food waste, trucking, septic water, so all that. So the wastewater treatment plant does not have to lose revenue because their municipal inflow water is reduced. So they might explore other revenue sources.
Right, the Greater Lawrence Sanitary District, that is, yeah. They're very progressive.
Yeah, and that our study showed that it's on the cost side, on the environmental impact side, so both are beneficial doing the co-digestion.
Thank you for the comment. It's a related kind of benefit, and the ways that these systems integrate. And I don't know if people caught it in the chats and the comments, but we are still sending the mixed liquor suspended solids to the municipal infrastructure. And because we're not generating enough solids on these smaller facilities to really digest and produce energy from a digestion standpoint. So it's better for us to send those organics and that mixed liquor suspended solids to the centralized infrastructure, where they have larger volumes and they have the benefits of bringing in additional food waste and mixed waste organics, and they can co-digest that and create energy from it. So it's a very symbiotic relationship where we don't need sludge holding tanks. We don't have to send in hauling trucks to take that sludge out. We can manage that mixed liquor suspended solids, send it to the centralized infrastructure. They can digest it down there, and we don't need the sludge holding tanks with the decentralized infrastructure.
But as part of work we did for presenting to the MWRA, and Shung did the analysis, was of showing there's a net decrease in the VOD load to the treatment plant because of the upstream reuse. So that, there's not an issue of them receiving what they do receive, but it is slightly less. So that then less aeration requirements downstream at their end, a potential for savings. There's a larger analysis that we worked with the Charles River Watershed Association on, can we have water reclamation and thermal energy recovery systems, throughout the MWRA service area, and that study had some greenhouse gas emission analyses as well as cost analyses that showed it basically is a similar cost of doing the replacement over time of distributed systems over the centralized system, similar cost, and about the greenhouse gas benefit, but also they were looking at an ecological benefit of, if you're using the reclaimed water for irrigation and groundwater replenishment, you could be improving the water quality that was impaired by all the stormwater runoff and lack of infiltration and lack of recharge of the natural wetlands and Charles River. So there's also a range of benefits that can be given, and doesn't all the water does not have to be used for in-building uses or irrigation. You could also do groundwater replenishment in a case-by-case basis. We got 4 more minutes. Any other questions? Anyone want in the chat?
Bruce, I was gonna ask,
Go
because we have a couple of closing things too, that if each of the panelists just had a closing thought that they wanted to close with.
Mike, go ahead. You want to kick it off? Mike's working on his tan. I will go ahead and kick it off, and Mike, you can go. Oh, go ahead, Mike.
That's not my tan, that's the lighting.
So go ahead. What was your closing thought, Mike?
No, go ahead.
Oh, okay. I would just say that thank you for joining. It's great to see everybody this early on the East Coast and even early on the West Coast. I see some West Coast attendees. So thanks for joining. I think it's a really timely discussion. I know one of the comments was about Texas and what's going on in Austin, and thoughts and prayers to those folks. But every time we have a challenge, whether it's Superstorm Sandy, whether it's the fires out in California, whether it's the weather that we're seeing in Texas, it just points more and more to there's not one solution that fits all. We have to work together. We have to integrate our centralized, decentralized infrastructure. We have to integrate our water and our energy infrastructure to get through these changing times. And so I think these are parts of the solutions, and there's more out there, and we need to continue to work together, educate one another, and move that forward. So that's my closing thought.
So yeah, I just want to thank the panel for inviting me. This is one of my first ones involved in your open discussion. So this was great. And yeah, sustainability is real, and reuse water is going to be a thing. You're going to see pop up more and more. Water is becoming more and more expensive, very, very expensive commodity. And just know to use all your resources when you decide where you're going to put that water, where you're going to use it for, so that you don't compromise another process for the savings that you're receiving from the initiative. So thanks. Great.
So I'll do next. Yeah. Again, thank you for the panel for organizing this event. Thank you for inviting us. And also thank you for everyone, joining and, listening us, go through all the work we have done. So talking about the thermal energy recovery for the reuse system, I think this is a great opportunity in the future, especially when we're going to see more and more decentralized on-site reuse water system, emerging in the big city like New York City, San Francisco. And a combination of thermal energy recovery really a beneficial thing that brings down the cost of the system and reduce the energy consumption and further reduce the carbon emission from the treatment system. So I think it has a great future that requires a lot of research and development. So yeah, that's my closing thought.
Okay, so are we still on? I'll go to that last slide, Meredith. I just, while we're bringing that up, I'd just like to thank some folks behind the scenes, Jim Newman, Diane Tufts, Melissa Mattis have been sort of my background helpers, Ethan with and Bob on site. Greatly appreciate it. And here's some websites to learn more from the DOE about the Water Energy Nexus, Living Future Collaborative, and Built Environment Plus. Really appreciate all the people, the participants have been fantastic. I think that's what makes this successful is your participation. So thank you for coming.
Thanks, Bruce. Thanks, everybody.
Meredith, we all set?
Sorry, I was on mute. I was just giving a big shout out to Bruce for pulling this all together and his team at Natural Systems Utilities and for their support. And then I also wanted to just let you know that we have a couple really exciting courses coming up, a half-day session on buildings and carbon that Jacob Rakusin is giving. It can be free for companies with under 100 employees. Ask me for more information. And we also have given by Brent Ehrlich at Building Green is doing an intro to healthy materials, which will be followed by an in-depth healthy materials course, also free for companies with under 100 employees, but open to everyone coming up in March. And don't forget to fill out the CEU form if you haven't done that yet. Thank you, everyone. And I did say, and this is all going to be up live on our website within the next few weeks. The other two sessions are already up there. So if you missed either one of those and want to go back and learn more about the recovery system, the wastewater systems, and learn more about the Kern Center, it's already up on our website. Thanks, all.
Thank you, Meredith.